Hello everyone, welcome to my civil engineering YouTube channel. Please subscribe to it and hit the bell icon to get notified when I post my new videos. So in my previous lecture series, I had discussed regarding how to analyze a frame in a non-sway condition, and also I had discussed regarding how to analyze a continuous beam using moment distribution method. Today, I'll be discussing how to analyze a portal frame using the moment distribution method with a sway condition. So, the procedure for analysis of a frame using moment distribution method depends on the type of frame that is being analyzed. Frames are always categorized as based on the condition as sway or non-sway frames. So based on the displacements. So the procedure for analysis of non-sway frames are similar to that of continuous beams, but as in case of analysis of the sway frames, the procedure is different, and there are two stages which are basically involved in the analysis of the sway frames. So they are namely non-sway stage and the sway stage. So these stages are described as stage 1 of sway analysis as a non-sway analysis stage. So in this stage we are going to first assume there is an existence of an imaginary prop that prevents the frame from swaying, and then we are going to compute the horizontal reaction at the supports of the frame, and we are going to note the difference between the reactions, that is a horizontal reaction between the supports, and that is noted as S. So this force is the one which is responsible for prevention of the sway. So I just repeated, when we come to the non-sway analysis of a portal frame, so there are two stages basically. One is the non-sway analysis stage, so second one is a sway analysis stage. So in case of non-sway analysis stage, we are going to first assume there is an existence of an imaginary prop that prevents the frames from swaying, and then we are going to determine the horizontal reaction at the supports of the frame, and then that difference between the horizontal reaction between the support is taken to be considered as S. So this force S is responsible for prevention of sway. So next stage is stage 2, that is called as sway stage of analysis. So in this sway stage of analysis, we are going to assume an arbitrary movement which acts on the columns of the frame, and the magnitude of these moments will always vary from column to column as in the proportion of I by L square. I just repeated, we are going to assume the moments which acts on the column of the frames, and these moments will vary from column to column with the proportion of I by L square. And then the arbitrary moments are then distributed for the non-sway condition. So as of by using the moment distribution table, how we are distributing the unbalanced moments, so same way we are going to do as that of the non-sway condition. So the third step is that we need to calculate the magnitude of the horizontal reactions. We need to calculate the magnitude of the horizontal reaction at the supports for the sway condition, and the summation of these reaction will give rise to arbitrary displacement. So that displacing force is taken to be considered as S1. So that force we are going to consider as S1. So we are going to calculate the magnitude of the horizontal reaction which are acting at the supports for the sway condition, and summation of these reactions, the summation of the horizontal reaction will give rise to the force, displacing force. So that force is termed to be as S dash. So and then the next step is we need to determine the ratio of S by S dash, where S is nothing but it is the horizontal reaction, the existing difference in the horizontal reaction, which is the force which is responsible to prevent the sway, and is obtained from the non-sway analysis stage. And S dash is nothing but the summation of the horizontal reaction which is responsible for the displacement. So the ratio of S by S dash will give rise to a factor which is called as a sway factor. So next step is that we use the sway factor and multiply with the distributed moments, so that we will get a corrected moment for a sway. So the last step is that we are going to obtain the final moments for the frame at which are the summation of the moments which are obtained from the non-sway stage as well as corrected sway stage. So final moments is nothing but the summation of the moments which are obtained from the non-sway stage and then the corrected moments which are obtained from the sway stage. So this is what the procedure which is adopted for analysis of the sway, analysis of the portal frame in the sway condition. Okay, so I have taken an example, the numerical, for easy understanding of the analysis. So here I have taken a portal frame ABCD, wherein A is a fixed end and D is the hinged end, and then B and C are the joints. So wherein AB and CD are not loaded with any type of loading, but BC is loaded with a uniformly distributed load of magnitude equal to 30 kilonewton per meter with a span of 6 meters, and the moment of inertia for AB is equal to 2I and also equal to BC, that is equal to 2I, and for CD it is equal to I. So the length, the span distance for AB and BC is equal to 6 meters and that of CD is equal to 3 meters. So next, first step, as we have discussed in the earlier, that is the procedure for solving the sway frames, is the first step is that we are going to analyze by using the non-sway condition first. So in the non-sway condition, the first step is we need to determine the fixed end moments. So as in case of AB and CD, it is not loaded, therefore the fixed end moment for AB, BA, CD and DC is equal to 0 since it is not loaded. So next is the calculation of fixed end moments for span BC. So MFBC is equal to minus WL square by 12 since it is loaded with a uniformly distributed load, and I am going from left side of the span, so it is nothing but the anti-clockwise movement, so therefore it is a negative variation, so it is equal to minus WL square by 12. So minus W is nothing but 30 kilonewton per meter, so W is taken in the form of kilonewton per meter, and length is taken in the form of meters. So minus 30 into 6 square divided by 12, it comes on to be minus 90 kilonewton meter. So this should be kilonewton meter. So next is calculation of fixed end moments at CB span. So as in case of the span BC or CB in concern, it is loaded with a uniformly distributed load. Therefore, for the fixed end moment at CB, it is nothing but the positive variation of the fixed end moment at BC. So therefore, it is nothing but W plus WL square by 12. So if I just solve that with W as 30 kilonewton per meter and L as 6 meters, so I'll get the overall fixed end moment as plus 90 kilonewton meter. So this is all about the calculation of fixed end moments with the non-sway analysis and concern. So the next step is determination of the distribution factors here. So here I have a table here. So you can just observe in the diagram wherein the portal frame has two joints here. One is joint B and joint C. So for which I need to find out the distribution factor with for the originating members. So if I just take joint B, so BA and BC are the two members with B as origin. So I just repeated, with joint B, members are BA and BC with B as origin. So therefore, if I just consider with B as joint, BA as member, so A is the farther end for B. So I just consider B as a joint, BA as a member. So A is the farther end for the B. So if in my previous lecture series I had discussed regarding how to take the relative stiffness when the farther end are of different support conditions. So in this case here the farther end is fixed end here. So in this case, if at all if the farther end is the fixed end, so in that case the relative stiffness is equal to I by L itself. So here as in case of BA member, I is equal to 2I and L is equal to 6 meters. So therefore I by L will be equal to 2I by 6. So if I just simplify that, it is equal to I by 3. So the next member with the joint B is equal to BC. So B is the joint, BC is the member with B as origin, and C is the farther end. So C is a farther end wherein it is a continuous support. So continuous joint. Whenever the farther end is a continuous in nature, so in that case the relative stiffness is again equal to I by L itself. So here as in case of BC member, I is equal to 2I and L is equal to 6. So therefore it is equal to 2I by 6. So therefore if I just simplify that, it is again equal to I by 3 itself. So if I just want to calculate the total relative stiffness for joint B with BA and BC as two members, so I need to summate both the relative stiffness, that is I by 3 and I by 3. So that is equal to 0.67I. So next thing is determination of the distribution factors. The distribution factor is nothing but it is the ratio of K by sigma K. It is the ratio of K by sigma K. So here K is nothing but for BA is for member BA, K is nothing but I by 3. It is nothing but equal to 0.33I itself. So divide by sigma K here is 0.67I. So it is equal to, if I just divide that, so I'll get the distribution factor for BA member with B as joint as 0.5. So say similarly, if I just solve for the distribution factor for member BC with B as the origin, so I will get again the distribution factor as 0.5 itself. So next, coming on to the next joint, that is joint C. So there are two members which are originating from joint C, that is CB and CD with C as origin. So here if I just consider member CB, B is the farther end for C, where it is of continuous nature. So as I said that when the farther end is continuous in nature, so in such case the relative stiffness is equal to I by L. So here I is equal to 2I, L is equal to 6. So therefore it is equal to 2I by 6. So if I just solve it, I will get the factor as I by 3 itself. So I will get the distribution factor as I by 3. So next, coming on to the next step, that is CD for member CD. So it is equal to relative stiffness I need to calculate. So D is the farther end for C. D is the farther end for C, wherein D is the hinged support. So whenever in order to calculate the relative stiffness, if the farther end is hinged in nature, then the relative stiffness is taken to be considered as 3/4 of I by L. So whenever if the farther end is hinged support, then the relative stiffness is considered to be as 3/4 of I by L. So here 3/4 times of I here remains I itself, L is equal to 3. So therefore if I just solve that, it is equal to I by 4 here. So again if I want to calculate the total relative stiffness, so it is nothing but summation of I by 3 and I by 4. It is nothing but 0.583I if I just solve it. So finding out the distribution factor, so it is nothing but K by sigma K for joint C with the member CB and CD. So by solving that K by sigma K with joint C and member CB, I have got a distribution factor as 0.57, and for CD member I have got it as 0.43. So The next step is the moment calculation of moments by using the moment distribution table. So here we can just observe that there are the members AB. The members are AB, BA, BC, CB, CD and DC, wherein the distribution factors are for only two joints with member BA, BC, CB, CD. So for BA and BC is 0.5 and 0.5. So for CB and CD is 0.57 and 0.43. So next step is fixed end moments here. So fixed end moments only for the BC and CB have calculated. So rest of the members, since they have not loaded, so for the rest of the members it is equal to 0. So therefore it is minus 90 and plus 90 for BC and CB. So next procedure is I need to distribute these moments. So if I just consider for the joint B, so it is nothing but the summation of moments at BA and BC. So 0, 0 plus minus 90, 0 minus 90, so 0 plus of minus 90, so it has comes on to be minus 90 itself. So minus 90 is the unbalanced moment wherein I need to distribute it between BA and BC as per the distribution factors. So if I want to counteract that minus 90, so the balanced moment should be equal to plus 90. So plus 90 into 0.5 if I do, so I'll get as 45 plus 45, and also for BC as plus 45. So that is the balanced moments for BA and BC. So next, coming on to the next joint, that is joint C with CB and CD are the two members with the distribution factors 0.57 and 0.43. So again, if I just calculate the moments, total moment at two joints, that is two members, that is CB and CD, so it is equal to 90 plus 0. So therefore 90 plus 0, it is equal to plus 90 itself. So the balanced, I need to balance the unbalanced moment of plus 90 by using minus 90. So minus 90 into 0.57, if I do that, I will get what is the amount of moment which has to be distributed for the member CB. So that is equal to minus 51.3 here. So again similarly minus 90 into 0.43, if I do that, I will get it as minus 38.7. So this is the distribution moments for CB and CD. So this is the distribution moments for CB and CD. So next step is I need to carry over the moments which are distributed at the joint members. So therefore I need to carry the moment from BA to AB, so with the same sign convention. So half the moment I should carry this. So 45 divided by 2, it is equal to 22.5 here. So again from BC I need to carry for CB. So it is again 45 by 2 with the same sign convention. So it is 22.5 once again. So 51.3 is there here with a negative sign. This should be minus 25.65, half of the moment with the same sign convention from CB to BC I have carried. So here coming on to the span CD and DC, so I have observed that D is the support wherein it is a hinged support, wherein the total moment is equal to 0 whenever the support is either simple support or the hinged support. So since the fixed end moments have got here as 0. So therefore there is no carryover option for DC here. I need to retain this 0 as it is. So next step is I have got the carryover moments here. So next is I need to balance this unbalanced moments at the joints first. So therefore minus 25.65 is there at BC, which I need to distribute it for BA and BC equally by using the distribution factors 0.5 and 0.5. So minus 25.65 into 0.5, if I do that, I will get plus 12.82. This has to be plus. It has written as minus 12.82. It has to be plus 12.82, and this is also equal to plus 12.82 because minus 25.65 is the unbalanced moment, which has to be balanced by plus 25.65 itself, and which are distributed as per the distribution factors for the respective members. So next is 22.5 I have here. So this 22.5, which has to be distributed as per the distribution factor of 0.57 and 0.43. So it is equal to 22.5 into 0.57. If I do that, it is equal to 12.82, and 22.5 multiplied by 0.43, if I do, it is equal to 9.68 with a negative sign, because 22.5 is the positive unbalanced moment. So next is after getting this balancing moments, I need to carry over for the members from BA to AB with the same sign convention but the opposite moment, that is 12.82 divided by 2, it is 6.41 with the same sign convention. So again from BC to CB it is minus 6.41, and then from CB to CD CB to BC it is minus 6.41. So for DC I am going to retain the same as it is. So I need to repeat this procedure so till I get the smaller amount of balanced moments. So smaller amount of balanced moments I have got here 0.07 and 0.06, 0.68 and 0.52. If I want to continue further, I can do it until 0.01 or 0.02. Very smaller moments I need to get. So until that I need to continue this procedure, and then I need to stop that. Further, after getting the final balanced moments, so I need to add all this from the beginning of the starting of the moment calculation. So I need to add all this to get the initial moments at each members. So here I have got for AB as 31, so BC as BA as 62.2, and BC as minus 62.2, and CB as 51.91, and minus 51.91 for CD, and DC it is equal to 0 as it is. So DC it has to be equal to 0 since it has a hinged support. So next is this was the non-sway moments which is due to the non-sway condition. So the next is I need to determine the sway moments. So sway force I need to determine here. So in order to determine the sway force, so as I know that there are two supports here, that is A and D for overall portal frame in concern. So since A is a fixed end, so I have the reactions here as one horizontal. So I have the reactions here, one horizontal, one vertical, and a moment here. So similarly for D support, again I have one vertical and one horizontal, since it is a hinged support. So if I just consider this, I need to calculate the horizontal forces here first. So I need to calculate the horizontal force at A, that is equal to HA. So HA, if I just take the the AB span here. So AB span, this is a AB span wherein there are two moments at AB span which have been calculated by using the non-sway analysis. So one is due to AB, MAB and MBA. So HA will be equal to MAB plus MBA divided by 6. So MAB plus MBA divided by 6. So both are in the clockwise direction. Itself. So this is also in the clockwise direction itself. As per the moment distribution table, what I have got the answer, both are positive variation. So I have taken it as same here. So 31 plus 62.2 divide by 6. So divide by 6. So I have calculated the value here. So HA is equal to 15.54. I have got 15.54 kilonewton. Similarly, HD is nothing but moment at CD plus DC divided by the overall span of CD. So that is equal to 3 meters. So MCD plus MDC divided by 3. So MCD I have got it as minus 51.91 by the non-sway analysis moment calculation by using the moment distribution table. So MDC I have got it as 0. So minus 51.91 divided by 3. So it is equal to 17.3 kilonewton with a negative variation. So these are all the sway force which I have determined by using the non-sway moments. So next is I need to calculate what is the overall sway force which is overall sway force which is used to prevent the overall force which is used to prevent the sway force. So that is nothing but S. So S is nothing but the summation of HA plus HD. So HA I have got it as 15.54 and HD I have got it as minus 17.3. If I just solve that, I have the difference in the horizontal reaction, the difference force in the horizontal reactions as minus 1.76 kilonewton. So this is what the amount of force which is used to prevent the sway force. So the next step is the sway analysis. The second step in the sway analysis is the sway stage analysis. So here MAB is equal to MBA. So MAB is equal to MBA. So that is equal to minus 6 EI delta divided by L square. So minus 6 EI delta divided by L square. Why? Because A is the fixed end here. So therefore in my previous lecture series I have discussed why it is minus 6 EI by delta divided by L square. So here this is the sway moments. So here 6E into 2I, I is equal to 2I delta divided by 6 square. L is nothing but 6. So divided by 6 square. So MAB is equal to MBA. So that is equal to minus EI delta divided by 3. Similarly, I need to calculate the sway moments at CD and DC. So since D is the hinged end, so it is equal to 3 EI delta divided by L square. Whenever the support is fixed, then it is equal to 6 EI delta divided by L square. Whenever the support is hinged, one end is hinged and one end is fixed, so it is equal to 3 EI delta divided by L square. So 3 EI, I remains I itself, delta is constant, and I is I, and L2 is equal to 3. So 3 EI delta divided by 3 square. Again MCD and MDC is equal to minus 3 EI delta divided by 3 itself. So here you can just observe that as in case of sway analysis, the calculation of the moments, we are going to take the only for the columns, not for the beam here. So next step is I need to find out the ratio of this. So the ratio is equal to MAB by MCD or MBA by MDC. So if I just take the sway force ratio, it is equal to 1 because both the values are same. So with this, if I just solve for the sway moments by using the moment distribution table here. So sway moments, the members are the same moment distribution table I have got here. So the forces, the members are AB, BA, BC, CB, CD and DC. So distribution factors remains the same, which I have calculated by using the non-sway analysis. So but here for the columns I need to assume a fixed end moment here. So since it is minus EI delta divided by L, I have got the values. So therefore for the moments in concern with AB, BA, CB and CD, it will be the same value with the negative moments. So I just assume the moment as minus 100. I can assume any of the moments, even I can take it as minus 1 also. So I just am assuming the value here as minus 100. So the initial value will be equal to minus 100. So for only the columns AB, BA, CD and DC. So here since D is a support wherein it is a hinged support, I need to make the moment equal to 0. So therefore minus 100 should be balanced with plus 100 so that the overall moment is 0, and this plus 100 moment should be half carried to the span CD with the same sign convention. So it is carried with plus 50. So therefore the initial value of the moments is plus minus 100 minus 100. So there is no moments here, BA, BC and CB, and then this is minus 100 plus 50, it is minus 50. So then it is 0 here. So next is I need to balance this unbalanced moment at the joints. So at BA and BC I have minus 100 here. So minus 100, there is no, at BA I have minus 100. So BC I don't have any moment here. So BA and BC should be distributed with a moment of minus 100. So I need to compensate that moment as plus 100. So in order to balance that, so minus 100 into 0.5, minus 100 into 0.5 will be 50 with a negative sign, but in order to balance that minus 50, it should be plus 50. So it is plus 50 and plus 50. So next is I have only 50 here with negative sign convention here at CD. So this minus 50 I need to balance for CB and CD with the positive variation. So plus 50 into 0.57. So it is plus 28.55 and plus 21.45. So then the next step is I need to carry over these moments. I need to carry over these moments from BA. Half the moment I need to calculate with the same sign convention. So 50 divided by 2 is 25. So similarly from CB to BC it is 14.28. So from BC to CB it is 25. And then since DC is the member wherein the D is the hinged support wherein there is no carryover business is there here. So therefore it should be 0 as it is. Next I need to again balance this with the for the joint members by taking the opposite sign conventions, and then I need to carry over for the next step. So these procedure will be continued until I'll get the balanced moment with the smaller variation. So here for the end moments what I have got the balance at the end I have got it as minus 0.04 minus 0.035 minus 0.07 for CB and minus 0.055 for CD, which is very small enough. So I need to, after that I need to stop there and I need to calculate the moments from the initial value to that of the balance. So if I just add all these moments, so I'll get the moments by using the sway force as minus 76.92, minus 53.86, minus this should be actually minus 53.86. This should be actually positive. So next is 38.83 minus 38.83 and 0. So these are the values which I have got by using the sway analysis. So these are the moments values I have got using the sway analysis. So the next is the sway force calculation. So for the sway force calculation, I have the sway force as S dash. So S dash is nothing but the summation of the reaction which gives the arbitrary displacing force. So S dash plus HA plus HD is equal to 0. S dash is nothing but the arbitrary displacing force. So S dash plus HA plus HD. So HA plus HD I have the formula as MAB plus MBA divided by 6, and for HD as MCD plus MDC divided by 6. So S dash is equal to MAB. I have got the value from by using the moment distribution table as minus 76.92 and MBA as 53.78. so same values I need to substitute here and get the value of S dash. So next step is, after getting the value of S and S dash, I need to find out what is the sway correction factor. Sway correction factor is nothing but the ratio of S by S dash. So S is the value which I have got by using the non-sway analysis, that is equal to minus 1.76 I have got. So S dash is the value which I have got right now, that is equal to 34.72. If I just substitute that and get the ratio, I have got it as minus 0.05. So minus 0.05 is the sway correction factor. So again, in order to determine what is the corrected sway moment, I have a table here. So wherein first is the member, second is the non-sway moments which I have got in the first moment distribution table. Third one is the sway moments which I have got right now by using the moment distribution table and by assuming minus 100 as the initial moment. So corrected sway moment is nothing but sway moment multiplied by K. K is nothing but the sway correction factor which I have got by using the previous slide, that is S by S dash. So which is nothing but minus 0.05 which I have got. So corrected sway moment is nothing but sway moment here multiplied by K. So sway moment for AB is minus 76.92 multiplied by minus 0.05. If I do K value is minus 0.05. So if I do that, I will get the value corrected sway moment as 3.846. So similarly, minus 53.86 into minus 0.05. So I will get 2.689. So similarly for BC, 53.86 into minus 0.05, so minus 2.689. So next one is for CB, 38.83 into minus 0.05, it is minus 1.942. So for CD it is minus 38.83 into minus 0.05, it is 1.942, and for DC it is 0 into minus 0.05, it is again equal to 0. So after getting the corrected sway moments, I will get the final moments by adding this non-sway moments plus the non-sway moments plus the corrected sway moments. So 31 plus 3.846, I have got it as 34.846. So then 62.22 plus 2.689, it is 64.909 minus 62.2 minus 62.689, so it is 64.909. See 51.91 minus 1.942, it is 49.968 minus 51.91 plus 1.942, it is 49.968 and then 0. So these are the corrected sway moments which I have got as the final moments. So last step is the bending moment sketch. So these are the bending moment values which I have got, the final moments, that is 34.84, 64.909, minus 64.909, and then 49.68, minus 49.68 and 0. So first thing I need to draw the bending moment diagram. Bending moment diagram I need to draw as first the portal frame. So AB I have got it as plus 34.846, which has to be the right side variation, and then minus 64.909 I have got it. So this is the variation, and then 64.94909, 49.968, again 49.968 and 0. So these are the bending moment sketch. So I just join it linearly. So apart from that, I need to find out the maximum moment for BC span, which is having the uniformly distributed load. So BC span, the maximum bending moment is equal to WL square by 12. So W is 30, L is 6 meters. So 30 into 6 square divided by 8. Sorry, WL square by 8. So 30 into 6 square divided by 8. If I do that, I will get it as 135, which is the parabolic variation which I have got. So I have incorporated in the bending moment diagram here itself. So this is all about the sway analysis of the portal frame by using moment distribution method. Thank you for watching. So if you just like it, please subscribe this video and share among your friends. Thank you.